Hello, everyone, and welcome back to a new episode of Advent of Code 2016. In fact, the last episode of Advent of Code 2016. Here we are on Christmas Day. Merry Christmas. It's not Christmas anymore because I'm not releasing these on the day that the puzzle was out, and I'm a little bit behind. But we're about done here, so I guess let's just get started. I guess I should mention that I have solved this problem already, but we're going to be looking at the solution. Day 25, clock signal. You open the door and find yourself on the roof. The city sprawls away from you for miles and miles. There's not much time now. It's already Christmas, but you're nowhere near the North Pole, much too far to deliver these stars to the sleigh in time. However, maybe the huge antenna up here can offer a solution. After all, the sleigh doesn't need the stars exactly. It needs the timing data they provide, and you happen to have a massive signal generator right here. This is the first I'm hearing, by the way, of the fact that we didn't need all these dang stars. Why do stars have timing data? It doesn't make sense. You connect the stars you have to your prototype computer, connect that to the antenna, and begin the transmission, but nothing happens. You call the service number printed on the side of the antenna and quickly explain the situation. "I'm not sure what kind of equipment you have connected over there," he says. I hope you guys appreciate the silly accent. "But you need a clock signal." You try to explain that this is a signal for a clock. No, a clock signal. Timing information so the antenna computer knows how to read the data you're sending it. An endless alternating pattern of 1 0 1 0 1 0 1 0 1. He trails off. You ask if the antenna can handle a clock signal at the frequency you would need to use for the data from the stars. "There's no way it can. The only antenna we've installed capable of that is on top of a top-secret Easter Bunny installation, and you're definitely not..." You hang up the phone. I don't know how well that accent all came out. I wasn't planning to do that, but I got to some quotes and I was like, all right, let's better find an accent quick. So, not a lot of practice with that, but we'll see. I think that was kind of a Jersey thing, maybe? I don't know. I've never been to Jersey, so it's a terrible caricature, I'm sure. You've extracted the antenna's clock signal generation SMBunny code, your puzzle input. It looks mostly compatible with code you worked on just recently. This antenna code, being a signal generator, uses one extra instruction. There's this instruction out x, which transmits x, either an integer or the value of a register, as the next value for the clock signal. The code takes a value via register A that describes the signal to generate, but you're not sure how it's used. You'll have to find the input to produce the right signal through experimentation. What is the lowest positive integer that can be used to initialize register A and cause the code to output 010101 forever? Okay, well, time to get looking around. Here's our puzzle input. And I spent quite a bit of time thinking about, rather than actually writing any code, I was trying to see if I could figure out what this program does myself and see if I could maybe reverse engineer like what the answer should be. I was able to figure out a number of things that are happening here. First of all, A gets copied directly into D, and then we sort of work with D for a while, and then put D back into A. I'm not really sure. So if we had just this line and the one above it, oh, that's right. No, we're modifying D a bit. Okay, so anyway, this whole thing here is the multiplication loop that we've seen a number of times, right? We are multiplying together B and C, 11 and 231, and adding the result to D. Okay. And then we copy D back into A. So it's like, why did we copy A to D and then multiply together B and C, adding them to D, and put that back into A, as opposed to just doing all the work in A in the first place? Well, it's because, I believe, let me just double check, line 9... Line 30, yes. So this line here, when we reach it, jumps back up to here, copying D into A. So D is keeping a copy of our puzzle input plus the product of 11 and 231. And we never modify D again in here. D is left alone forever and never read except for copying it back into A. So this is like the main loop of doing everything. That runs here. And you can also see something interesting. Oops. So we copy D into A, then we copy A into B, and 2 into C. So, in fact, I think, copy D into A and A into B. So, if we ever reach this line, then a second time, that is, then we'll redo exactly what we did the first time with no differences. We can tell because we're resetting all the registers to the same state. D gets written to A, and D hasn't been changed since last time we were here. A gets copied to B, and this jump non-zero does nothing. It's a no-op, of course. And 2 gets copied into C, so that's A, B, C, and D, all the same values they were before. So that seems pretty good. So my conclusion is that something mysterious happens in between this line here and these two. And sometimes we jump back only 19 lines to this copy, and then we do some outputs that are not the same as what they were before. And some other times we reach the bottom, where we unconditionally jump back to here, which starts the loop again, looping exactly the same output. Now, what I couldn't figure out just by inspecting the program is like how many times stuff is being written inside. Basically, all the rest of what is inside this loop was quite a mystery. We're somehow, I think, comparing two numbers, like B and C, maybe. But I couldn't figure out the details of how that works. 'Cause we're sort of like, we have this loop here of like, if C is non-zero, then we skip to this line. And if C was 0, then instead we run this thing, which gets us to 1, 2, 3, 4 to output. So, meanwhile, we're decrementing B and C. I don't know exactly what good that does. Like we're also jumping back by 1, 2, 3, 4. I don't know. So it looks to me like there's some kind of comparison of B and C going on in here, but I couldn't figure out the details. And there's a lot of jumps going on that make it hard to put together exactly what's happening. So, all right, having inspected all that, we found out a few interesting things. One of which is that it should not be the case, I believe, that we will ever enter a loop in which we're outputting zeros and ones in the right order, and the registers are changing. That is, every time we're in that loop, the registers should like go back to what they were. That was one thing I was worried. So, okay, now let's start talking about how I might solve the problem. The first thing that occurred to me was perhaps a little bit over-elegant, or over-involved, was to say, okay, well, let's keep track of all the states the computer has ever been in, and if it ever returns to a state that's exactly the same as one it's been in before, same instruction pointer, same values in every register, then we'll declare the computer to be in an infinite loop, and the puzzle is solved. That was the right input. That was a little bit awkward to do. One reason for that is that the registers are stored in a map, and maps are not good hash keys. Like, that is surmountable. We could get around that if we had to. But also it would mean storing just a whole ton of possible states, and it seemed like there would be problems with that. Maybe it would have worked, but I didn't try it. The other thing is, like, what exactly, how do we even implement out? Let me look at my git log here. Yeah, okay. So there are, whoops, git log of this. I forgot how many. I guess I only did a couple things. So yeah, day 25, I just copied the whole interpreter, and then or the first one of those. Let's grab this commit here. Okay, now we'll go look at the source here. So I removed all of the stuff from the interpreter about toggling because we don't need it anymore. And I added this. I replaced the toggle instruction with out, but I didn't implement it. I just wanted to be able to parse the program and see what's going on. We left the optimizations in here because, as you saw, there was a big multiplication loop at the beginning. And of course, you know, I had to change the parser, which was just this. Still have this regex parse in here. I don't know. We should get rid of it. But again, I'm in the middle of Git archaeology, and it's going to be a pain. So let's not. So I just created the computer and then said print out the program to make sure I had parsed it right. So that's fine. But now the question is, like, how do we implement out? The thing that appealed to me the most as like what I would like to do is to have the computer yield a series, basically turn the computer's run program into a generator, where it yields a series of output values, and then in main we run the computer and iterate through its output values and decide at some point whether we're done. I think that is the cleanest approach, but it's not what I ended up eventually doing. I thought it was going to be more complicated than thinking about it now. I actually think it would have been. Because I was thinking there's a lot of programs, or a lot of instructions, and like having them each yield either an empty list or a thing like might have been complicated. But I think it's actually not too bad because no instruction ever runs another instruction as a result of calling apply. And even if it did, that wouldn't be such a huge problem. So the idea would be, in all of these apply methods, to just return this, basically, right? Or not yield anything. I'm not sure exactly how it works if you try to yield. If you try to, like... Yeah, I think we'd have to return something iterable anyway. So we would do that inside of J and Z, copy, and so on. And then out, we would yield an actual value. And in computer, we would say, we would just yield the result of this. Yield from, I guess, or actually, we'd have to loop over the results and yield each of them. But that's a thing we could do, and it might actually be pretty cool and clean to have done it that way, but I didn't. What did I do? Well, let's check out, I guess actually what turns out to be my final solution. I could have just checked out master, huh? Let's do that. Oh, good. You guys have been looking at the right thing this whole time. It's a Christmas miracle. So what I had out do is a bit, I think, unclean. So I gave the computer class an additional field, which is what output we want to get next. So it starts out as 0, and whenever we out a 1, we'll set it to... Whenever we out a 0, we'll set it to 1. Whenever we out a 1, we'll set it to 0. And if the value that we out is ever not the value we're expecting, we throw an exception. Not so pretty, but I think that part of getting the hang of Python is coming to grips with their, as I understand it, style of using exceptions more for control flow. I would never, ever do it this way in Clojure. Maybe not in Haskell? I think it would be pretty clean in Haskell to just yield a series of ints, but Haskell's kind of exception-like mechanism of using either or maybe or something might be reasonably clean as a way to do it, so it wouldn't be so outrageous. But on the JVM, like, the style of using exceptions is not at all like this, so I wouldn't do it. In Python, I think this is a reasonable style? I don't know. Anyway, so I check if the value is the one we wanted, and then, assuming that it was, then I toggle the computer's expected output by calling not on it, and then converting that to an int. I could have written like it's equal to 1 if it was 0, otherwise 0, but like, I don't know, this seems reasonably clear. And so the computer class, of course, had to change a little bit. The first change is that it has this expected output that I start out at 0, and I also put an instruction count in here. Because I didn't end up implementing this thing that checks whether you've reached the same state twice, how am I going to know? Like, let's say we output 1,000 zeros and ones, well, we'll never get to a condition that says, oh, you failed. Like, if we find the right puzzle input, I guess is what I'm saying, then the out instructions in the program will never throw that exception, right? So we need some other termination condition. And what I chose to try was to say, all right, let's just not run. We'll try running the program for up to, I forget, like 10 million instructions or something. And if it hasn't thrown an exception after 10 million instructions, it's probably in an endless loop outputting the right stuff. Not a formal proof, but we can at least get an answer that's worth trying, and then feed that to the web page and see if we were right. And so I had to change run program to basically it adds to the instruction count, and if it was indeed greater than 10 million, we say yes, correct, this was the right input. Otherwise, we run the program, and if it throws an exception, we return false. Or we run a single instruction, and then return false if there was an exception. So that means main has to handle the result of calling the computer as a program, and we basically just iterate over all the integers and construct the registers starting at 0 and then set a to 1 to I, and run the program. And if it returns true, then we print the value that made it return true and break. So this runs reasonably quickly. I think it would probably run 100 times faster and still get the right answer if I were to remove... Like I just reduced this from 10 million to 100,000. And I think that makes it run quickly enough that it's reasonable to watch it. I don't know. Yeah, that's still the right answer, 189. So I guess it's not actually 100 times faster because not all of the work was done in writing this. I don't know. I also tried some intermediate steps of making the out instruction actually print to the screen a number, and I sort of looked at what was happening, but it was just like a bunch of... It looked to me like a bunch of random ones and zeros that were not the right ones for inputs other than this. And there wasn't any clear pattern to me of like how they were converging. But I suspect there's something clever where like the lower the input is, the longer... I don't know. I think it probably started with like a bunch of random-looking numbers in a loop, and then a smaller number of random-looking numbers in a loop, and eventually, like that, as you get up closer and closer to 189, the size of the loop shortens and shortens until it's only 2 characters left. But I don't know. I'm just speculating. Who knows? So at any rate, that's the... Let's just commit this change. Weaken termination condition. Okay, cool. So let's go and see how this does on the web page. Yay! Okay, so we got puzzle answer part 189, or answer was 189, and just like in the 2015 Advent of Code, the very last puzzle, the part 2 is just, hey, you get a free star. So all you need is the 50 stars, the antenna is ready, but you look and notice that there's a star installed at the top of the antenna, only 49 more to go, and we actually have 50, because we have the other 49 and there's one, so we can press the button to retransmit the signal. I've already transmitted the signal. The first time it didn't say retransmit. It said you can transmit the signal, but we're now going to retransmit it. Very exciting. Now there's snow everywhere. It's a very pretty Advent web page. Anyway, you activate all 50 stars and transmit the signal. The star atop the antenna begins to glow. Suddenly, you see the sleigh fly past you. Looks like Santa was already waiting for your signal. And then he has a nice little congratulations. You finished every puzzle in Advent Code 2016. I hope you had as much fun solving them as I had making them for you. I'd love to hear about your adventure. You can get in touch with me via contact info on my website or through Twitter. So I could read Topaz's voice in the New Jersey accent for you guys, but I don't think there's any need to do that. And he's also, just like last year, in every day's explanation, there was some text not decorated at all, but if you happen to mouse over it, it had a little tooltip joke here. And so once you get all 50 stars, he highlights the little jokes for you, so you can mouse over them and read them. Okay, well, there you go. Let's go check out our calendar. And it's all animated, and we got Santa with his, what is that, 12 reindeer? I don't know about that. And the star thing is going off. And the town looks very pretty with the monorail and the Christmas tree and the snowflake on this building's wall and so on. So it's all very nice. And I'm afraid that means that this series has come to a close. There will not be any further Advent of Code 2016 episodes. You know, if this is the only thing on my channel that you've enjoyed, then that's fine. See you next year, probably. If you want to check out my other stuff, feel free. I mostly play games. Occasionally do a little bit of programming for Dungeon Crawl, but mostly I'm playing games and things. Sometimes programming games. At the moment, not at the moment. Starting tomorrow, new series of a programming-themed game called Hacknet. So, tune in for that if you're interested. But if you're not, that's fine. I understand. Thanks for joining me. And given you're here at the last episode, I think it's fair to say that you probably enjoyed it. At any rate, though, I hope you did enjoy it. Thanks for watching, and I'll see you next time.